In this video, we will be looking at motion of planets and how it's affected by the gravity in space. So first of all, we know that each planet is spinning on its axis, and this is called rotation. The planet that's pictured below is Neptune. And we know that Earth also spins on its axis at an angle of about 23.5 degrees from the sun. Now, orbit is the path that a planet follows as it travels around another body in space. So our orbit around the sun is called its revolution. Moons also orbit around planets. So a revolution is what we call one complete trip along an orbit. For Earth, that's 365 1/4 days. For the moon traveling around the Earth, that's about 27 to 29 days. Kepler was an astronomer who discovered 3 laws of planetary motion based on his study of the positions of the planets and their view from Earth. So we're going to look at what those 3 laws are. The first is that the orbits of the planets are elliptical. Ellipse is an oval-shaped path. So when we look at the Earth's revolution around the sun, we know that during part of its revolution it's closer to the sun, and another part of its revolution it's further away. When it's close to the sun, that is known as perihelion, and furthest from the sun is aphelion. And if you notice from the diagram, when we are in perihelion or closest to the sun, we move faster, and when we are in aphelion, we move slower. And the reason is because we cover the same amount of area at the same period of time. And you can see from the diagram how that changes. And the same is for all the planets. When they are in perihelion or closest to the sun, they're going to be moving faster through their orbit. Kepler's third law says that the planets that are more distant from the sun take longer to orbit the sun. For example, we know that Earth takes 365 1/4 day. Well, Mercury, which is the planet closest to the sun, only takes 88 days to complete an orbit or revolution, whereas Neptune, which is the farthest planet, takes 164 years to revolve around the sun. Now, Kepler knew that these 3 things were happening, but he could not explain exactly why it was that those planets further away were moving slower. It wasn't until Sir Isaac Newton and his laws of universal gravitation that we had an answer. You probably remember stories of Newton, from the apple falling on his head, making him think of the idea of gravity. Well, that story is not exactly true. And long before Newton, we understood the idea of gravity, that everything fell towards the Earth, but he was the one who provided a description of what it actually was. So although others had theories about the existence of this gravitational force, he was the first to formulate and test the law. So the law of universal gravitation says that the gravitational force decreases with distance, and the greater the mass of an object, the greater its gravitational force. So what that means, the closer we are to the sun, the stronger the force of gravity is, which is why the planet moves faster as it's closer to the sun. And the greater the mass of an object, the greater its gravitational force. Because the sun is larger, we're attracted to its pull of gravity as opposed to the other way around. Same thing, the moon is attracted to the Earth's force of gravity instead of the Earth attracted to the moon. The direction of the pull of gravity is always toward the center of mass. So when you're standing on Earth, the pull of gravity is towards the center. So no matter what side of the Earth you're standing on, you're not going to fall off. And so the same thing, we are attracted to the center of mass of the sun. So when we're orbiting the sun, it's actually the center of the sun that we are orbiting. All right, so if gravity is pulling the Earth to the center, why don't we just move into the sun? Why do we continue to move in the circle? Well, there's a couple of reasons. If there were no forces acting on the Earth, or the forces were balanced, then we would continue moving through space at a straight line. Think about if you throw a baseball in outer space, it's going to keep flying in a straight line forever because there's no gravity pulling on it, there's no air friction stopping it. Whereas on Earth, if you throw a baseball, it's going to fall to the ground because of gravity. It's also going to slow down because of air friction. So the Earth, though there's no friction in space, it's going to continue to move, but the sun's gravity pulls it towards the sun, keeping in that circular orbit. So it's always trying to move past the sun, but the sun's gravity is pulling it sideways. And you can see that from the diagram here. The Earth wants to keep moving in a straight line, but the gravity of the sun is pulling it, so we kind of cut that angle, and the resultant path ends up being that elliptical or circular orbit. Inertia is what keeps an object in motion as long as there's no outside forces. So we define it as an object's resistance to change in speed or direction until an outside force acts on the object. So with our baseball in space, it's going to keep flying in a straight line forever as long as there's no air friction or gravity pulling on it. So same thing happens with the planets around the sun, or here you can see the moon, which orbits around the Earth for the same reason. Inertia is what keeps it in motion because there's nothing acting on it. There's no air friction in space. Space is a vacuum. But the Earth's gravity pulls the moon towards the Earth, so it keeps it in that circular orbit. All right, so a couple of other ideas. Gravitational attraction keeps the planet in their orbit. Inertia keeps the planets moving along their orbits. That's why they don't stop or they don't get pulled towards the sun. There are no other forces acting on Earth besides inertia and gravity from the sun because there's no friction in space. The attraction of gravity between two masses, like the sun and the Earth or any other planet in the sun, remains the same as long as the distance between them stays the same. And so the Earth must move in a circle or elliptical shape to keep that same distance from the sun. The force which keeps an object moving in a circle is the centripetal force. If you've ever ridden a roller coaster and gone upside down around that loop, you can actually feel that force. That's what keeps you in the car from falling to the ground. All right, one other thing, because the planets closer to the sun move faster than the orbits of the planets further away, at certain times of the month, it appears that planets that are further away actually move backwards. So if you look at this diagram right here, if we assume that this is Earth and Mars, when Earth passes Mars, it appears that Mars moves backwards with respect to the Earth. And you can see, follow this line here. This is what Mars's movement looks like from Earth. So another diagram of what that would look like looking down on it. You can see that as we pass Mars, it almost looks like it loops. That's called retrograde motion. It's the apparent westward or backward motion of the planets. And that's it for motions due to gravity.